going to introduce a very important notion, that is the expectation of a random variable. Now consider the following game of rolling a dice once. It is a fair dice, so I am just rolling it once. I know my sample space here is going to be any one of the outcomes, and the outcomes are 1, 2, 3, 4, 5, 6. I am talking about a 6-sided fair dice. Now let us play this game. If the outcome is even, you lose an amount equal to the outcome. If the outcome is odd, you win an amount equal to the outcome. My outcomes are 1, I lose, it is odd, so I win an amount of +1. Outcome is 2, I lose an amount. So if I win, I am going to put a +1. If I lose, I am going to put a -3, again it is odd, so I win +3, 4 is even, I lose -4, 5 is odd, I win +5, and 6 is even, I lose -6. So there is an element of chance, and I can tabulate or summarize my outcome as I term my negative winning is a loss, positive winning is actually a gain. So these are my outcomes. So the question we are asking here is, would you play this game? An intuitive answer to this is, I will play if I am a rational thinker. If I am a rationally thinking person, I will play a game only if I am expected to win this game. So I am again telling something about expectation. So now let us go and analyze this problem from a probability point of view. So I want to know whether I should play this game. So I am going to just roll the dice 100 times. Once I roll a dice 100 times and observe the outcomes, so you can see that I have 100 outcomes which I have summarized here. So this is the first outcome was a 1, second outcome was a 6, so fourth my 100th outcome was a 3. So here what I do next is I observe how many times or the frequency distribution of these outcomes. I note down 1 appears 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 times. My 1 appears 16 times. So similarly, I plot the frequency distribution for each one of these outcomes. 1 appears 16 times, 2 appears 10 times. From the frequency, I can obtain the relative frequency. This is something which we have already seen how to get it. And in addition, I am going to see that from the frequency and relative frequency, I can compute what is my average winning. That is, I know that +1, my relative frequency is 0.16. I find out what is the average. We also know how to compute the averages, and you can check that the average winning is -0.09. So I am actually, the average winning is a negative. So this might say that, okay, you don't play the game because it is negative, but again it is not that negative, so I might be tempted to play the game. So I continue the experiment. I roll the dice for 1000 times. Now when I roll the dice for 1000 times and I count the frequency, again I repeat the experiment. Now you can see that 177 times I had a 1 appearing, 177 times a 2, 167 times a 3, 153 times a 4, 163 times a 5, and 163 times a 6. I count the number of times each outcome appears. Again I compute, you can see the relative frequency which I have computed here. And if you compute the average winning, it is -0.451, which again tells me that in total or an average, my winnings is negative. So, it does not help me or does not give me an indication of a positive gain. So, I might not decide to go ahead and play the game. Now, you can notice something here. This 0.16, 0.10, 0.21, all these relative frequencies which I have here, the relative frequency when I roll for a longer number of time, and you can recall what was the probability mass function of the outcome of a die. I had the following 1, 2, 3, 4, 5, 6 with probability 1 by 6, 1 by 6, 1 by 6, 1 by 6, 1 by 6 and 1 by 6. So, you can recognize that what is stated as the relative frequency is precisely this 1 by 6, or it is very close to this 1 by 6. In other words, the probability of the random variable, which is the outcome, taking a value I which was equal to 1 by 6, I going from 1, 2, 3, 4, 5, 6 is the same as the relative frequency. This is something which we observe. So, if I have x, so I can state x takes my value 1, 2, 3, 4, 5, 6 with the probability x equal to I 1 by 6, 1 by 6, 1 by 6, 1 by 6, 1 by 6 and 1 by 6. Now, if I am looking at this as winning, so let me take it as y takes the value 1 minus 2 plus 3 minus 4, 5 and minus 6. These are my winnings. So, I can see that in expectation with the same probability, or let me call this x and I can call this y, it does not matter to me. So, so I can see that this relative or my average winning can be rewritten as 1 into 1 by 6 minus 2 into 1 by 6 plus 3 into 1 by 6 minus 4 into 1 by 6 plus 5 into 1 by 6 and minus 6 into 1 by 6, where these 1 by 6 are the weights associated with the values the random variable is taking. So, it suggests, what does it suggest? That if I repeat rolling the dice for a very large number of time, then my average gain would be the following, which is minus 0.5. I repeat. So, it suggests that if the relative frequency is close to 1 by 6, that is what we see, and if I repeat rolling the dice for a very large number of times, then the average gain would be minus 0.5. This is very close to what was our average winnings of 1000 rolls of a die. You recall the average winning of 1000 rolls of a die was minus 0.451. So, here you can see that the expectation of a random variable, I can define the expectation of a discrete random variable. Suppose x is a discrete random variable which takes values x1, x2, x3 and so forth, countably infinite with the respective probability x1, probability x equal to x2, so forth. Then the expectation of the random variable is x1 into probability x takes the value x1 plus x2 into probability x takes the value x2 and so forth, which can be abbreviated as summation I going from 1 to infinity xi, probability x equal to xi. If x takes finite number of values with the same probability, then I have the expectation of x is equal to xn into probability x equal to xn. So, this is what we refer to as the expectation value of a random variable we also refer to as expectation of x, and it is written or it is denoted by E of x. The expectation of a random variable can be considered to be the long run average value of the random variable in repeated independent observations. So, if I am rolling a die, then expectation of the random variable can be viewed as a long run average. Let us look at a few examples to understand this concept. Again, I roll a dice once, I know the sample space is 1, 2, 3, 4, 5, 6. The outcome is 1, 2, 3, 4, 5, 6, equally likely with this is the probabilities. So, from my definition, my expectation of x is xi, probability x equal to xi, summation I going from 1 to 6, which is going to be 1 into 1 by 6 plus 2 into 1 by 6 plus 3 into 1 by 6, 6 into 1 by 6. So, I can take this 1 by 6 out, it is 1 plus 2 plus 3 plus 4 plus 5 plus 6, which I can say is 7 by 2, which is 3.5. So, the expectation of this random variable is 3.5. So, now let us interpret this random variable. X is the outcome of a roll of a die. I am getting an expected value of x to be 3.5. So, would it be right for me to say that if I roll a die sufficiently enough number of times, then I will get an outcome of 3.5? The answer is no. It does not mean that if you roll a die once, you can expect the outcome to be 3.5. That is not what this 3.5 means. What it means is, if I roll a dice sufficient number of times, that is, I keep rolling a dice, then the average of a large number of rolls, you can expect that to be 3.5 in the long run. It does not mean that you will have an outcome which is 3.5. Let us look at the probability mass function. So, you can see that when you are looking at, so now if I summarize the rolling dice simulation, you can see in the relative and the relative frequency for 100 roll, the average was about 3.67, here it was 3.437. So, can the 100 rolls, will the average value be exactly equal to 3.5? Need not be. Here you can see it is 3.67, here you can see 3.47. So, you can see that it need not exactly be 3.5, it would be close to 3.5, both 3.67 and 3.437 are close to 3.5, and expectation or the expected value of x is the notion of a theoretical average, and you can see that when you are actually conducting the experiment of rolling a die, I could get values which are not exactly 3.5 but close to 3.5. So, let us look at a random variable which I am rolling it twice. Again, recall we defined this random variable as the sum of outcomes. We saw that this was the distribution of this random variable. It takes values 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 with these probabilities. So, now the question is, if I continue to roll a 2 dice for sufficiently long period of time, what can I expect the average of the sum of outcomes to be? Again, expected x gives me the answer. So, I look at it, it would be 2 into 1 by 36 plus 3 into 2 by 36 plus 4 into 3 by 36 12 into 1 by 36, and I can verify that this expected value of x is equal to 7. Notice that in the earlier case, the expected value of x need not be a value of x. It was 3.5. X does not take a value of 3.5. So, I am not saying that x can take a value of 3.5. We are looking at a average of these outcomes. Whereas here x is taking a value which it is already taking, which was value of 7. It can happen, it need not happen also. So, expected value of x is 7. So, I can interpret or articulate it by saying that when two dice are rolled over and over again for a long time, then the mean sum is 7. Now, interestingly, you look at the probability mass function, you see that the distribution was in a sense symmetric around this 0.7, and also you can see that suppose you imagine this to be a rod with weights hanging, that this point in some sense balances the rod. So, if one of the physical interpretations of the notion of expectation is the center of mass expectation, which comes from physics. This I am not going to dwell more into it, but it is just an intuition. You can think of these as weights being laid on a unitless scale, and you can see that this point actually balances the weight. Now, let us look at the experiment of tossing a coin thrice. Again, we know this is our sample experiment and this is the distribution of the random variable. So, my expectation of x in this case is going to be 0 into 1 by 8 plus 1 into 3 by 8 plus 2 into 3 by 8 plus 3 into 1 by 8, which is going to be 3 plus 3 is 6 plus 6, which is 12 by 8, which I can see is 3 by 2. Again, I can see that expectation of x is 1.5. It is not a value which x takes, but it is a value between 1 and 2. Again, the way I can interpret this value 3 by 2 is if a coin is tossed 3 times and I repeat this experiment over a long period of time, the mean number of heads in 3 tosses is 1.5. Does not mean, and I should not interpret it as the number of heads would be 3 by 2 or 1.5. This does not make sense, but the mean number of heads in 3 tosses is 1.5. Now, again going to the probability mass function, I know that this was again symmetric, and you can see that the mean is somewhere here, which is 1.5. This is 1, this is 2. These two are same, and you can imagine that this acts like a fulcrum which balances the mass. Now, let us look at a special random variable which I refer to as a Bernoulli random variable. So, a Bernoulli random variable is a random variable which takes two values. For ease of exposition, I just assume that it takes the value 0 or 1. It takes only two values, and the probability with which it takes the values, I am going to say it takes a value p, it takes a value 1 with probability p. Since this should add up to 1, if it takes the value 1 with probability p, it should take the value 0 with probability 1 minus p. So, this is the probability mass function of a Bernoulli random variable which takes two values 0 and 1. Now, if this is the probability mass function, then the expectation of this random variable, it is taking the value 0 with probability 1 minus p and value 1 with probability p, it is equal to p. So, the expected value of a Bernoulli random variable is equal to p. Now, if it is equally likely that x takes the value 0 and 1 with an equally likely probability, then I know that this p equal to half, which tells me that the expected value of x equal to half. So, if p is equally likely, then p equal to half, in which case the expected value of the Bernoulli random variable is equal to half. Again, you can see that this does not take either of these values, but it is balanced between. So, x takes two values 0 and 1. So, the balance is at this point half. There is another random variable which we refer to as a discrete uniform random variable. So, this again, suppose x takes the values 1, 2, 3 up to n, and the chance of it taking any value is the same. Earlier Bernoulli took only 2 values, but here I am assuming it takes n values. So, the chance it takes the value 1 is equal to the chance it takes the value 2. So, each one of them have a probability 1 by n. All of them add up to 1, we can verify that. So, the probability distribution is given by x takes the values 1 to n with the probability 1 by n, 1 by n, 1 by n. What is the expectation of a discrete uniform? So, it takes discrete values 1 to n with equal probability. So, my probability mass function, if it takes the value 1, 2, 3 up to n, all of them are going to be, so you can see that all the bars would be of the same height, hence it is referred to as a discrete uniform distribution. What is the expectation of this random variable? So, again it would be 1 into 1 by n plus 2 into 1 by n plus so forth n into 1 by n. I can remove 1 by n is common, 1 plus 2 plus n, which we can see is 1 by n. The sum of n numbers is n into n plus 1 by 2. I cancel these two out and I get a n plus 1 by 2. Hence, you can see that the expectation of x is nothing but n plus 1 by